Hey, everybody, we're going to get started. So if everyone could just sit down. So I'd like to thank everyone for actually showing up in the rain to come to the seminar series. We're going to have a great talk by Professor Sam Clark over here. But before we get to that, first I'd like to do acknowledgement of country. The ARC Training Center in Predictive Breeding acknowledges the traditional owners and their custodianship of the lands on which we meet. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country, and we recognize the valuable contributions to Australia and global society. So I'm Karen. I'm a gene editor over in CCS and Coffee, and I'm going to facilitate today. Just a few things. The seminar is going to last about an hour. We have 30 minutes afterwards for tea and coffee, but please hold off. It is recorded, so please be mindful of that. If you do have any questions for those on Zoom, please don't use the chat function, use the Q&A, and there is a way to like certain questions if you want them to go to the top of the list. Sorry, can't think of the word. Okay. Today's speaker is Professor Sam Clark. He's a professor of animal breeding and genetics at UNE. His research projects center around genetic evaluation and genomic selection in beef cattle. These projects contribute to the creation of reference datasets for productivity, meat quality, and feed efficiency, methane outputs, and animal health and welfare to enhance national genomic selection programs. Sam is also a research theme leader at the UNE node, or he's the UNE node leader of the ARC Training Center in Predictive Breeding. And I'll hand it off to him.
Thanks very much, Karen. So yeah, thank you very much for having me today. It's really nice to have the training centre that brings animal breeders and plant breeders together in a way that we can all share ideas. And coming to do a presentation today is really part of that process of coming together to talk about our different experiences and how we can share that between the different areas. So today I'm going to talk about reference populations, and reference populations to people often mean different things. If you think of training data sets and reference data sets, it's really the data that we use to essentially make genomic predictions. And it really is what makes genomic predictions accurate, what makes them inaccurate in some cases, or biased or unbiased. So we want to take a bit of a deep dive into, well, how does this data set creation, how do these reference populations impact genomic selection? Now, we've been working on these questions for quite a long time, so I'll try and use my experiences from animal genetics, so around projects creating reference populations, so that we can essentially think about how they might be put into some plant breeding contexts as well. The other thing I'd like to do is acknowledge Julius van der Werf. So Julius has had a lot of experience in this space as well. He's a professor of animal genetics as well at UNE. And he's been responsible for a lot of the conversations and a lot of the work over the last 15 years between him and myself around reference population design. So a little bit about me. So I did an undergrad Bachelor of Rural Science at UNE in the early 2000s. I'm from an agricultural background. We have a farm with beef and sheep. So I'm quite an agricultural person. I didn't really ever think that I'd be in a system, that I'd be an academic at a university thinking about how can I potentially find the best animal to select. So I did an undergrad. I actually thought, oh man, not really sure that academia or anything associated with academia is for me. I went and worked for Westpac Bank for a couple of years. Then I realised, whoa, banking, that's kind of not for me either. And I really liked quantitative things. So I came back and did a PhD in quantitative genetics, and here I am. I've stayed in quantitative genetics. Now, often I try and think, well, why did I stay in quantitative genetics? Early on, I started to realise that quantitative genetics is just about variation. So variation is everywhere. Variation in human height, variation in animal performance, variation in plant performance. That is the core for everything we do as animal and plant breeders. What we have to do is try and make tools to try and see, well, is that variation genetic? Does it get inherited across generations? Can we use it in breeding programs? Can we select parents and then we keep getting this genetic progress? So I saw that this variation exists and it is actually a really long-term powerful tool to improve agriculture. So stayed here, kept working in animal and plant breeding, and hence why we're here today. So today I'm going to really try and link what happens in animal and plant breeding. Of course, I'll be talking from my perspectives as working in animal breeding programs and genetics behind animal breeding programs primarily. And I'd really like to think that you guys can think, well, for this concept about, say, relatedness of a reference, Sam's talking in an animal context. What does it mean for me in a plant context? And is he talking about a variety when he's talking about a sire line? Is he talking about just a step in the breeding process, or is he thinking, actually, it's something very different? So try and take home today what you can think from an animal perspective, if you're working in plants, how you could think about some of the concepts we talk about today in plants. I really want to build up information from the basics of a breeding program and think, where does a reference population sit? So we have a little bit of basics at the start, and then we'll really get into how can we optimize reference populations? What are the factors that we have to consider when we're optimizing reference populations? I love to start presentations with a quote, and this quote really resonates with me as an animal breeder, because when we're thinking about variation, the only way to understand variation is actually to measure something. If it's not measured, we're kind of making it up. It's all based on kind of innuendo, opinion. Those things change over time. Whereas if we start to measure something, then we can manage it. And in a breeding program, we can make genetic progress. If we don't manage it, then of course, we don't make any genetic progress. Now, a little bit of background about the quote. So Peter Drucker was a management consultant for many of the early big companies in America. He has a number of books around how to manage businesses. And I think breeding is often thought of something different, but at its core is a business. And that's why I've really chosen a business quote this time, because breeding is a business. How do we make it better? We measure. And we have to do that all the time. And core to measurement is a reference population. It's essentially just measuring individuals to understand variability between them so that we can predict other individuals or other lines. So let's think of some basics for some context. So most breeding programs all have the same structure. They start with a plan, which we often call a breeding objective. We measure some information based on that plan of what we've said is important. We then try and utilize that information that we've measured and evaluate it so we get the most value from those measurements, find the best parents, select them, and then the new generation occurs. It's really a simple process when you think about it. We just plan, measure, evaluate, select, and go round and round and round. Now, if we were thinking about what tasks happen at each of those plans, there's quite a bit of work associated with the planning component. We call that the breeding objective. That's, of course, the traits that we want to measure and we want to improve. Sometimes there's traits that we want to improve that aren't measured. So we'd start to think, well, is there something that's quite correlated to those traits that still allow us to make genetic progress in those areas? We then have to get our hands dirty, do some field work and undertake some measurements, whether that's in a plant context where you're measuring different cultivars or different varieties in a field trial, or an animal context where animals being run in a contemporary group where they're born and raised together. Once we've taken those measurements, we have to then evaluate them. And that's where estimated breeding values come in and genomic selection comes in. And really, I think of them as how to get the most value out of the work that someone's done in the field. Because essentially it's trying to connect all of the measurements that are taken over time between different cultivars that may be genetic related or different animals that are genetic related, and providing the most accurate estimate of their future breeding potential. So then we select. We have to, in animals, often be a little cognizant of that inbreeding can occur. So we can't select too few parents. So we have to balance that. Some plant populations, we have to do that too, like in trees. In other populations, inbreeding is used as a tool to control uniformity. And at that selection stage, we really try and focus on that. Then, of course, we have around and around and around we go. Really, most breeding programs are centered around our breeders' equation, where we really want to have accurate selection. We want to select as few parents as possible and do it as quickly as possible. Now, that's where animal breeding and plant breeding are often connected, is via this breeders' equation, where we're really trying to say, we want to pick the best. We want to make sure that we've got genetic variation. We want to actually make sure we accurately capture that genetic information and do it as quickly as possible. And sometimes different tools and different technologies get embedded in the breeding program for different reasons. But most of the time, it might be because it might explain variation a bit better. It might be more accurate. It might be quicker in the breeding program. Not all technologies have the same impact to each stage in that breeders' equation. So now we're connecting animal and plant breeding. We've connected it with the breeders' equation, but historically, they've been quite different. So in animal breeding, there was a lot of history around performance recording and progeny testing schemes, and then to nucleus breeding programs in the late 80s, to genomic selection in the early 2000s. If we step across to plant breeding, there was the essentially reinvention of Mendel's laws in Sweden in the early 1900s, where they found different cultivars had different traits essentially, and bulk breeding systems were set up. And they've evolved to pedigree breeding systems and single seed descent systems like Lee uses with his different projects, to now to genomic selection as well. And we can see that if you follow kind of a funnel, it's all centers now to genomic selection. And that's what's really connecting animal and plant breeding, is this ability to use DNA information to try and make genetic predictions. Now, okay, we've got genomic selection. I thought, oh, okay, well, maybe I can make a joke here. I say, what if you put a Dutchman, an Australian, and a Scotsman, but Mike's not Scottish, he's Australian, but he spent a lot of time in Scotland, in a room together? Well, they create genomic selection. And really, genomic selection has been the superhero of quantitative genetics for the last 20 years. It was first suggested back in 2001, but it's really evolved to essentially commonplace in most breeding programs now. From something that was a suggestion based on simulation in a paper in 2001, that we could use genetic variants that cover the entire genome to make it a prediction of genetic merit or breeding value, to something that's being utilised in most breeding programs. It's quite an amazing thing to have been part of. So what has been the promise of genomics? If I'm thinking from an animal breeding context, the promise of genomics really centres around early accurate predictions. So early accurate selection, often prior to when you could have got a record on an animal. Because if it's easy to get a record on an animal at an early age, well, there's not a whole lot of difference in the breeding programs. But if you can't get information early and you can't get it accurately, genomic selection has revolutionized those types of breeding programs. The kind of pin-up boy for genomic selection has been the dairy system. The reason is that you can't milk a bull. And so it takes a long time for you to figure out how good a bull is for milk production. What you have to do is you select the bull, you make some daughters from that bull, you then milk the daughters, which can take many, many years. And for progeny testing schemes in dairy, it might have taken 8 or 9 years to get a relatively accurate prediction. Whereas if you build up a data set for a prediction of milk performance, and you can predict maybe a little less accurately, but a lot earlier, you can make a lot more genetic progress. And so a lot of the early papers around genomic prediction were really centered around solving that problem in the dairy industry. So if you have looked at literature, it all started in that spot, and then it's been applied to every breeding program that we can think of. But let's think of it from where is the core benefit? It's really this early life prediction or early process prediction. So if you're thinking in plant breeding, when we're generating a new line or a new cultivar, it's really in early stages of the breeding program, we make accurate selection decisions so that we don't just have to take a sample of these lines to to yield trials. We actually have some selection prior to that. Okay, I'll get to the point. Yep. It's the time to start talking about reference populations. So what really is a reference population? So if we think of it in a traditional structure, a reference population is merely animals that have been recorded for a trait or a group of traits preferably. There's some knowledge about the genetic relationship between those animals and your selection candidates, and that there's some knowledge about how that data was collected. So are they in the same paddock or are they in the same yield trial, so that we know some background things that might bias our predictions. So really, there's always been reference populations. So in animal breeding, there's a long history of keeping a pedigree and performance recording. The animals with records and a pedigree were essentially the reference population. Now, what genomic prediction and genomic technologies, so that ability to take a DNA test, have been, is you now are no longer constrained to really close relatives. So for pedigree breeding, close relatives are what really gives accurate selection. That's what progeny testing schemes have been centered around for a long time. Because if you think of the relationship between a selection candidate and their progeny, it's very high, but it's also kind of validating the breeding value. It's observing what happens in progeny. That's what we want to do in the breeding value anyway. So we're recording really close relatives for a progeny testing scheme. Whereas for a general reference population for genomic selection, we're no longer constrained to those close relatives. We can now think of it as a population, and then the opportunities start to stack up. You think, oh, I don't have to just record sibs or progeny. I can actually record any animals as long as they have something valuable to the prediction, as long as they have some sort of value to help me predict my selection candidates. So that flexibility of who, what, and when to record becomes part of the breeding process now. We can start to design reference populations rather than just harvest data and give some outputs back. So what does it mean in, say, a plant breeding context? If we think of the reference population for a plant breeding context, if we look at the bottom left or bottom right as you guys look at it, the reference population really is lots and lots of metadata. It's yield trials over a long period of time. And most of the time, that's at the end of the breeding cycles. So it's size of a yield trial, whether it's 2x5 or something like that. And it's just lots and lots and lots of plots. We've all seen those cool pictures Lee puts up. Okay, so we've got these late stage yield trials that are there to try and predict either earlier stages or even early parental crosses, to think, well, what would be the value of crossing two varieties before I've even done it? And so we really want to think, okay, if I'm designing a reference population, one, do we observe all the variation we need to in those late stage trials? And two, do we often make decisions with genomic prediction early on? So is it about the parental cross, or is it early on in that single seed descent type period? So where could we start to try and build information as well as where can we use information? Because generally genomic prediction has been used more as a tool. When could we use this information? So for example, in our single seed descent illustration here, we'd be thinking we might be able to use it in F2 to F5 because we can then couple some selection along with our building of inbreeding. And then we can stack different genotypes together and make fast genetic progress. And what I'd like to really make you think about today is, well, have we got the data to be able to underpin those predictions that you can use? And what are the opportunities that you can see within the different breeding programs that you work within to actually record information so that you can use it in those stages as well? So reference populations started to become more and more popular in animal breeding kind of around that 2007, 2008, 2009. The reason for that was there was quite a lot of funding for reference populations in some different breeds. So We have the GINFO herd, so it's genomic information nucleus in dairy. We had the Australian sheep information nucleus in sheep, which was the first information nucleus. And then there's other projects that have been run in the past. There's a Northern Genomics project, say here at UQ, it lives in the crowd. There's Southern Multibreed in the south. There's Repronomics. There's lots of animal breeding industry-based projects that are really centered around this reference population. Now, we've kind of transitioned from calling them information nucleuses or nuclei, to reference populations, but I kind of really like that idea of calling it an information nucleus because it centers and makes you think that actually what I'm doing here isn't about the prediction, it's about creating information. It's making sure that we optimize our recording strategies so we get as much information as possible. Now, if we think of where do we collect that information in an animal breeding program context, most breeding programs have a simple structure when we think of the breeding program structure. The top tier is the nucleus, and that's where most genetic progress occurs. But to make sure that you've got enough genetic material for commercial production, there also has to be a multiplication tier. And in plant breeding, that's when you're really trying to get enough seed for commercial producers to be able to plant in a field. In animal breeding, it's a little bit different because bull breeders or ram breeders are often part of both the nucleus and the multiplier tiers. Some of their bulls will go to become sires of sires, and some of the bulls will go to become parents of the commercial generations. And so it's not as clearly delineated as it probably is in plant breeding programs, because you have that specific breeding program where you create the variety, multiply the seed, and send it to commercial production. What does it mean when we start to think, well, where does the information come from? Traditionally, the information was in that nucleus. We're actually recording selection candidates or relatives of those selection candidates. When we're thinking of a reference population, it can sit to the side of that nucleus, mainly because the purpose is still to select the top animals. And in the nucleus, generally those top animals sit there. They're part of that nucleus. It opens up opportunities, not just for information, but it also opens up opportunities for genotyping lower tiers and opening up that nucleus. So a lot of, say, sheep breeding programs had work in the 90s and the late 80s around open nucleus schemes. It's often if you have a really large tier of commercial producers, and so that's where the big bulk of the population sits. Often, because you have such a big population, the normal distribution is nice and well formed. And so the top animals can compete with the nucleus animals. And you can make some extra genetic progress by upgrading those into the nucleus. And that's where open nucleus schemes can be quite valuable. Now, the limitation to open nucleus schemes was really measurement. Costs a lot to measure lots and lots and lots of animals. Having a reference population that enables accurate genomic prediction, it enables us to genotype essentially lower tiers and upgrade them to the nucleus if their prediction allows it. They say, you're actually a top animal, you can be put into the nucleus. So it's not just for getting information for selection, it can give us some more diverse information too. It can help with that diversity problem when we're trying to plan matings too. Now, a core thing about our information nucleus or a training data set or a reference population, they're all interchangeable terms, is that we don't just think of one trait. At the moment in beef cattle and in sheep, one of those traits is methane, and we have quite a lot of projects at the moment around recording methane in ruminants, whether it's beef cattle or sheep or dairy cattle. And one key thing is that we don't just record methane by itself, because then we've only got a reference population for methane and it might predict methane, but what about all the other traits that are important to a breeding program? And so it's really, really important when we're designing a reference population that we don't just look down a narrow hole, we actually look back and think, well, what are all of the traits that we need? How do we make sure that we have a whole bunch of information about the correlation between traits as well as the trait of interest that we're adding to our breeding program. So being broad in our reference population is really important, not just for single traits, many, many traits and many, many individuals. So then we started to think about, oh, how do we design reference populations? And there's been a lot of work around how can we deterministically predict how accurate a reference population will be at predicting a genomic prediction. So what is this accuracy of a genomic prediction given a certain population structure? And between lots and lots of different authors, and I just put a few up because there's heaps more papers than this, just because there's some familiar names to people here at UQ with Ben having a big role in a lot of those papers. Is really, in those papers, they were valuable to look at, well, what are some of the terms that we can start to think about? Is it the population structure, how diverse it is? Is it actually the size of the reference population, so the number of animals being recorded? Is it something about the variation of the given trait? And so most of those equations essentially rely on how much genetic variation is there, what is the effective population size, which is then translated into the size of the average size of a chunk of DNA, and then how many animals do you have in that reference. What you can see is reference population size matters. Of course it does. If you have a diverse population, we want to try and predict it, you're going to need more animals. And so often the papers that were done at that time, if you think about it logically now, it just makes sense, which is good. So it makes sense that you need a bigger reference population size if you don't have as much genetic variation, because if you think of it, phenotypic variation is not very genetic. And so if phenotypic variation is very genetic, you don't need many records to do it. So there's this link between the amount of genetic variation, or the heritability, and the size of the population. Now, those estimates were pretty crude at a population level, because you think, oh, let's think of a population. Does every animal have a chunk this long, and then the next chunk, and the next chunk, and they're independent, and they're all segregating so that we've got 100 chunks for that whole genome? Highly unlikely. There'll be close relatives in that population. There'll be distant relatives in that population. There'll be some chunks this long and there'll be some chunks this long, depending on the relationships between animals. And so there's started to be more and more work on, can we treat all data the same? So what we actually see is that chromosome segments, it's just not a single chromosome segment. There's not 100 chromosome segments when we look at different populations. There is a link between the size of the effective population size and the average size of the length of a chromosome segment, but it's not perfect at all. And so we see that some populations that aren't as diverse, of course, they have bigger chunks. So something like a Holstein Friesian, then definitely they have longer chunks than, say, in a merino breeding program. But there are in sheep, because there's lots and lots of sheep and they're not as well recorded as, say, in dairy cattle. So I think that's important to remember, okay? We've got to think of how does this population matter for the reference population? So I'm not going to be able to have the same concept for a dairy cow as I do for a merino sheep, as I do for a wheat breeding program, as I do from a pulse breeding program. So we're going to have lots and lots of different reference populations. But if you've got a big population size, you need more records. If you have a small population size, it's likely that you need fewer. So then we started to think, well, where does the information come from? In a traditional breeding program, information comes from relatives. So we started to think, well, do relatives still inform a genomic prediction? And really, of course they do. Relatives share bigger chunks in common. So if you've got big chunks in common, you can predict the relative relatively well. Okay? If you have small chunks in common, if you don't have enough data, you can't predict the small chunks. So we just tried to do some deterministic simulations, and this is some work that Julius did in the last few years, since 2019. He started to think, well, what if we have relatives versus a wider population, where does the information actually come from our genomic predictions? And we could say, okay, is it from direct relatives and we can get a certain accuracy of prediction, or is it from the wider population? So what we can do is we can say, well, direct relatives actually have a very small effective population size. It's just a little tiny subset of the population. And that would give you a certain accuracy of selection. And the wider population size would represent the whole population. And it would only give you a certain amount of accuracy. But sometimes that overlaps. So what we have done here is we have two sources of information, and we can say, well, direct relatives would get a relatively accurate prediction, and the wider population would too. And if you added those two information sources together, a relative actually gets quite a lot more. If we think of it in an animal breeding context, we often have relatives, and they're also part of a herd on a given farm or part of a given breeding program. But then there's a whole bunch of other people that have the same type of animals, whether it's the same type of pigs or the same type of, in my context, beef cattle, whether they're all Angus beef cattle, or they're all Wagyu beef cattle or Hereford beef cattle, or they're part of a big pastoral company's breeding program. So there'll be this structure that exists in that data. There'll be some close relatives, there'll be herd or flock mates, and then there'll be the wider population. And we started to think, well, how does the information flow? Do relatives matter? Can we just get a genomic prediction off the shelf and it's a one size fits all and everyone gets 50% accuracy at the first day of age? Or is there variability in accuracy from the data sets for each of the selection candidates? And so we modeled the same way. Different subsets of the population could have different effective population sizes with different numbers of records per effective population size. Because if you've got close relatives, it's likely that that's limited to some animals, in this case, 50 animals. In the own herd, say 400 animals, and then the wider population is many more animals. And you can see once we did that different sources of information contribute differently to the average genomic prediction accuracy. And often that own herd information is extremely important to the breeder in that herd, but it might only contribute a little bit more to the wider population. So if people often ask who should do the recording, because that's a question that we often get in industries where there's this dispersed nucleus and there's lots and lots of breeders, often the person that benefits most is the breeder doing the recording because they get the most accurate prediction, which will mean they'll make more genetic progress. Now, often that doesn't sit for some people. They go, oh, but I do all the work. What does it mean if I measure my own animals? Won't everyone else get benefit as well? Well, that's kind of right, because if you have a small population, it's really important to be related to it because you can get accurate predictions from a small population. So if we look at this table, what we really want to pay attention to is the difference between the population only and the all information. So if we look at the population only, when you've got a small reference population, so the top line of this table, there's a big difference between having all information, so information from your own herd and relatives, versus being part of the population. So in that context, when you've only got a reference population of 2,000 independent animals that have been recorded, having relatives matters. If you look at the bottom row, where we have 10,000 individuals recorded, the difference between the population and own information, and the all information, isn't very large. That's mainly because you've got so many more individuals, the impact of relatives isn't as big. So there's this interaction between relationship in the population and the size of the population and its value to predictions. So what we started to think of this term where you've got population only, we call that kind of the baseline prediction or the baseline prediction accuracy for a genomic test. It's what does everyone on average get in a breeding program. And what's above that is what relatives will give you. So we can see in the red, relatives matters more if the reference population is small. As you get bigger reference populations, then it doesn't matter as much. Now, if we take a look at This next table, it's the same structure, so smaller reference populations on the top and then larger reference populations on the bottom. But what we've varied this time is the number of relatives. So let's say you've got a bigger family size or a smaller family size. And so if you have big family sizes, on average, you get a pretty high prediction accuracy at a relatively small reference population. And that's what was observed in dairy cattle. When you only had 2,000 animals, maybe 2,000 semen-tested bulls as part of the reference population, you had pretty high prediction accuracies. It's because you're predicting all close relatives. But if you only have that for a relatively large population, on average, that's accuracy is quite a lot lower. Now, if you look, when we only have 10 relatives, the difference between all information and our population information is quite small, even for our small reference population, just because there's not enough relatives. Okay, so you can still have relatively inaccurate genomic predictions if your reference population is small. And I think that's the take home from these slides is if you have a population that is essentially a small effective size and you can record lots of relatives, it doesn't have to be a big reference population. But as soon as you want to make it more diverse, in beef cattle, we have a challenge. If we wanted to make predictions across breeds, so within breeds, we have quite small effective population sizes. As soon as we want to predict, say, 10 different breeds, say Angus and Charolais and Wagyu and Simmental, the effective population becomes much, much larger. We do a good job at within breed, but maybe not across breed. So we have to take that into account if we're trying to increase that diversity. We need to get bigger reference populations to do a good job. The other thing is there's never just a single accuracy for a genomic test. It's always dependent on the amount of information that you have in common with the reference population. I think if we start to think of relationship as that, then we can see if you have big chunks in common, then you're likely to have an accurate genomic prediction. If you don't, it's likely to be inaccurate. There isn't a one-size-fits-all accuracy. Okay, so if we have a less diverse population, we get higher accuracy on average, and the population accuracy does a really good job when you get a big population size in terms of number of animals recorded. Okay, so if we have relatives, then we get essentially a big bang for our buck for selection candidates. Our average accuracy is much higher than what we would if we don't have relatives. So that's where it's really important if breeders are trying to say who should measure. The person that gets the most value is whoever is closest related to your selection candidates. So often, say in a wheat breeding program where it's nearly constrained to a business, the business gets the most benefit out of a reference population because they're linked and they're trying to predict their own information. Now, if there's lots and lots and lots of other varieties that maybe, let's say they're a long way behind that variety in the business, or that don't really relate so well to their varieties, you might get an inaccurate prediction from that disconnected reference population. So reference populations are more accurate if they're connected to your selection candidates and that relationship is higher. If you get lots and lots of money and you can spend it on lots of records, well, then that becomes less of an issue. And unfortunately, that doesn't really happen. So we have to optimize our information. So we could think, okay, well, where do we get our information from? Is it research herds? Is it just breeder herds? Is it national variety trials? Is that the only spot that we get our information from? Then you have to think, oh, okay, well, what will be the value? When we work with RDCs like MLA, Meat and Livestock Australia, they're often around industry good goals. And the benefit for industry may be different if you are working with a pastoral company that has their own goals. So you may give different information and different information will have value. Often in beef cattle breeding and sheep breeding, we get asked, well, hang on, there's like 14 million beef cows in Australia and 27 million all up if you count all the production animals as well. Oh, why don't we just get an abattoir to record all of the commercial carcass information? And then we'll have 20 million records and we'll rule the world. Okay, so often that comes out. One thing to keep in mind is that link between the nucleus and commercial data. The other is that we still want to have unbiased predictions. If you can't separate environmental noise and the patterns of genetic variation, it becomes really, really hard to make accurate predictions. So I've got a couple of slides on what could be the impact if you are trying to record commercial data versus kind of semi-structured data from research projects. So when we think of, wow, is commercial data value? So can I rule the world? Can I get the abattoir to record the information for me? What we have to still think of, okay, how many animals are recorded? Yep, we've talked about that already. What's the heritability of the trait? The bottom two are the key for commercial data. What's the correlation between the recorded trait and the breeding objective? Sometimes, for some traits, commercial data may actually be closer to the breeding objective trait than what was happening in the nucleus. A really good example of that is in beef cattle, often to improve carcass quality and eating quality experience for consumers. We will use an ultrasound scan machine to understand how much fat is within the meat. We call it intramuscular fat. And that's essentially an indirect measure, a correlated trait to getting meat quality in a piece of steak to eat. Now, it's only correlated. It's not perfect. It's not our objective trait. The actual objective trait is from the carcass itself that can be observed from those commercial animals. So there are benefits sometimes from commercial data if you're closer to the breeding objective trait. One of the challenges is, oh, okay, what about how well will they be recorded? Over time, you think, well, in designed reference populations, often recording is more accurate. And so you have less biased predictions. So if you have accurate recording, what we could think of is the variation is more likely to follow the genetic pattern and heritabilities will be higher. If you have inaccurate recording, heritability is likely to be lower and you may be not capturing the breeding objective trait. And so you can then easily model it deterministically if you say, if you have a certain number of phenotypes at this heritability versus another group of phenotypes at another heritability. And often the biggest cost may actually be the genotyping. So if you do a really good job for a small number of records for your refined breeding program, it actually can be more cost effective than getting sloppy recorded data from a commercial system. That's assuming that the heritability is a bit lower. Now, if it was, it's probably pretty close though, because in commercial systems, if I think of in beef cattle, what generally happens is animals are born in big groups with a big calving interval. Then as they become closer and closer to harvest, they get shuffled into groups. So if I think big pastoral companies, they'll have multiple different breeding systems. All of their animals will be taken to a backgrounding system to prepare them for, say, a feedlot system. They'll be weighed into groups and they'll be all shuffled around. And then they'll go to the next one and they'll be all shuffled around based on their groups again. So we get this harvesting of data, which then often will reduce the heritability. It also increases the likelihood of biased breeding values. So when we look at that, we have to often look at our cross-validations to make sure that they're not biased. So we can always think of cheap phenotypes. We have to do a cost benefit to make sure it actually is a benefit to the business before just jumping at those million and going, I can rule the world. So that brings me to, if we could just harvest data and really be a quantitative geneticist in terms of animal breeding context, we've got kind of a bit lazy in that sense. We always just take data from breeders, make new breeding values. We think, oh man, look, we've got continuous data recorded over. Let's put a random regression to it. Okay, let's put a more complex quantitative model on top of that data. But what we can do now with reference populations is get back to that old statistical concept of linking design to prediction. And so if we can do that, we still have to think of basics of design of data recording. And in animal breeding, the effectiveness of performance is really linked to the size of contemporary groups. So if you have groups that have been kept together since birth and there's not a big range in age, because of course environments change over time. If you looked across 6 months, one born now and one born 6 months' time, it's a very different environment. So you want to have them as little constrained groups that have shared the same growing up experience. It's kind of like your class in primary school. And if you followed them all through, it means you have to stay with everyone in primary school. Imagine that. That'd be chaos. Okay, so that's what we want animals to do, so we have to manage that. We also have to manage, the number of parents that are represented in those groups. We can't just have our preschool made of one family, because that'd be hard work, but it would also mean that we wouldn't have any comparisons across families. And what we're trying to do in animal breeding is actually compare across families. So we have to make sure that there's a number of sires in those groups. If we think in southern production systems in beef cattle, often there's only single sire contemporary groups or only very few sires in the contemporary groups. We need lots of sires in the contemporary groups to get valuable data. If you think of it in a plant, I was trying to think, well, how do I put these concepts of effectiveness of performance, so effective number of records and representation of families? It's really, if you've got a block design, if you have not enough sires, that means you don't have enough diversity in the varieties that you're testing within your yield trial. And that will be really closely related varieties. And so you wouldn't actually observe the differences, even if they were large, because everything's quite similar. It would also be if you didn't have enough data. So effective performance would be, let's say, oh, hang on, I only want to do one block. I don't have enough data then to make effective comparisons. We actually want to make sure you got 6 blocks or multiple blocks in your design. And then you have replication of those different trials. So that's what I'm linking with our effectiveness of performance and the effective number of sires to our yield trials that have enough varieties and enough lines and replicated enough times across that environmental trial. Now, one of the challenges that often is more evident in plant breeding programs is that plants can't walk. Surprise, surprise, they tend not to be able to walk. Is this linked with the environment? So that G by E by M that comes with some of our predictions. And so the added context for plant breeding programs is those yield trials need to be replicated in different environments if you want to use them in those commercial environments. If you don't want to use them in those other commercial environments, then there's no point. But if you want your variety to cover across the whole range of the world and you rule the world essentially, then you have to test varieties across environments. And it's the same with different sire lines within breeding programs. Okay, so I'm running out of time. So what we want to really note is that when we're designing the reference population, we can use our relationships as a certain construct. And as we do a better job of designing our reference populations, we will want to refine the definition of a relationship, not just as an individual and how it's related to other animals with records, but actually regions of the genome that have certain amount of power to predict. And what you can do is then think, well, the left-hand side of the mixed model equation essentially tells you the amount of information that you have about a given region. If you solve it for regions, then you can say this region or that region has more information than another. And I think that's a really powerful way to think about designing a reference population, combining with a digital twin and simulating what could be the next generation, what potential haplotypes could be needed to be predicted, and how many of those are represented in our reference population. So that then we go and say, we need to record this line and that line. It may not be for performance. They may never become varieties that are marketed to the commercial system, but they have information that are valuable to predict different traits that might be important for the commercial production system. So we move this relationship from an individual to a chunk of DNA. And then when we start to combine that with selection and optimal contribution selection and stacking, like Eric has been doing as well, is then we can predict those chunks better. So then the accuracy of our stacking technologies become better too. So we need to move from this individual-based to a segment-based prediction. And of course, our relationships change from being either a pedigree-based or a genomic relationship. And we can look at the coefficients of our mixed models, which essentially the diagonal of the coefficients matrix tracks the number of records per class. And the inverse of that matrix helps us understand the accuracy of how well that piece of information is recorded. In animal breeding, we've always really looked at it at the individual level, but I think there's a real opportunity and there's technologies and tools like Bayes-R and different prediction models that are utilized that do it from a SNP-based model or a chunk-based model. And if we look at the accuracy of those diagonal elements from those interpretations of the mixed models, then we can understand how accurate have we predicted each chunk. So that's where digital twins come in. We can then simulate layers of the breeding program and generations of the breeding program to understand what's the probability that a chunk will occur and how often should I represent those chunks in my yield trials. It's not just about validating a product anymore. It's actually about having information to be able to predict that chunk. And so I think that's a really important progression that we need to make when we design reference populations, is to combine this simulation and prediction together. And that's kind of what a statistician would do. Think of design before you record the data. And I think that's a good spot to finish. I know I'm running out of time, Karen, so thanks for not giving me too many cross looks. And so we could do that with genetic algorithms. We can, which we already do when we try and optimize breeding programs. And the challenges with some of the technologies is around scaling those models. But with new ways to utilize data and AI and computing technologies, that's becoming less and less of a challenge. So we can optimize our coefficients matrix. So we optimize accuracy per haplotype, not just for optimizing matings, but also for making sure we've got information to predict certain chunks. Okay, so we're at the end. Hopefully you've got a better understanding of what a reference population is. I really hope that instead of you really thinking, oh, I know everything about animal reference populations, you've started to think, oh, hang on, what does that mean if I'm doing a wheat breeding program or a pulse breeding program or a canola breeding program, tree breeding program, beef cattle breeding program? How could I use some of the concepts to help our industry partners design the data sets that are recorded for information so that we have more accurate prediction? And then I think the final closing one is we want to try and optimize designs based on haplotypes and information known about different haplotypes rather than just on the individual level alone. Okay, thank you very much.